For this video, we are going to find a general solution to a system of linear differential equations with constant coefficients. So we've got x prime is minus 20 ninths x minus 8 ninths y, and y prime is minus 4 ninths x minus 34 ninths y. And we'd like to find a general solution to this system. And let's do this by applying our linear algebra techniques, finding the eigenvalues of the matrix of coefficients. So step one would be to set up our matrix A of coefficients when we write this in matrix form. So our matrix A would be the minus 20 ninths, minus 8 ninths on the top row, getting the coefficients for x prime, and on the bottom row we pull off the coefficients for y prime, which were minus 4 ninths and minus 34 ninths. And then our next step is to find the characteristic polynomial for this matrix. So to do that, we would take the determinant of the matrix we get when we subtract lambda from the diagonal. So it's going to be minus 20 ninths minus lambda. The minus 8 ninths we leave alone. The minus 4 ninths we leave alone. And the other diagonal term, minus 34 ninths, we subtract lambda. And when we take the determinant, that means we're going to multiply our two diagonal entries. So we're going to get the minus 20 ninths minus lambda times our other diagonal entry, which was the minus 34 ninths minus lambda. And then we're going to subtract the product of the off-diagonal entries. So that's going to be the minus 8 ninths times the minus 4 ninths. So that's what we would call the characteristic equation for this matrix. And we want to figure out when is that going to be equal to 0. So let's first simplify this a little bit. So grouping our terms together, we get a lambda squared plus 54 ninths plus 648 over 81. And we want to figure out when is this characteristic polynomial equal to 0. So that's the third step, would be to find the so-called eigenvalues, the values of lambda that make that characteristic equation 0. So this characteristic equation, we've got P of lambda is equal to lambda squared, and then the 54 over 9, that's just 6 lambda, and the constant term is 8. And that we can factor into lambda plus 4 and lambda plus 2. So this tells us our eigenvalues are lambda is equal to minus 4 and lambda is equal to minus 2. And therefore, we know what the values for R1 and R2 in our solution are going to be. We get that x of t is going to be some constant c1 e to the minus 4t and plus c2 e to the minus 2t. And we would have a similar looking solution for y, which would namely be y of t is equal to c3 e to the minus 4t plus c4 e to the minus 2t. And then the idea is these coefficients c3, they might depend on c1 and c2, and the same for c4 is that it might have some dependence on the solution that we get for x. So now that we've got our solution for x, we can use that to find the solution for y. I'm going to need to do that on a separate slide because I ran out of room. So let's head over to a separate slide. Okay, so trying to wrap this up, we were working with, on the previous slide, the system that we have over here, x prime, y prime. We found that the eigenvalues for the matrix of coefficients were minus 4 and minus 2. So I know that my solutions for x and y should have e to the minus 4t and e to the minus 2t. And so now I can do this in any one of different orders here. So for example, I could start with the top equation over here and plug my solutions or my proposed solutions into that top equation to see how C1 and C2 are related to C3 and C4. Okay, so using the top equation, we would need to find x prime. So that would be the minus 4 C1 e to the minus 4t minus 2 C2 e to the minus 2t. And therefore, using the equation that's circled in red, we on the left side, we would have minus 4 C1 e to the minus 4t minus 2 C2 e to the minus 2t. And that all is going to equal minus 29th x. So minus 29th x I can write as minus 29ths times C1 e to the minus 4t minus 29ths times C2 e to the minus 2t. And then we're going to add to that the y stuff, which would be minus 8/9 times y, which was C3 e to the minus 4t, and then another minus 8/9 C4 e to the minus 2t. And then we can group up our terms and find the dependencies on these. So taking all of the 4 minus 4t terms, this one, this one, and this one together would give me minus 4c1 is equal to minus 29ths C1 minus 8/9 C3. And then grouping all of the e to the minus 2t terms, that one, and that one, gives me a second condition that minus 2 C2, that needs to equal the minus 29th C2 minus 8/9 C4. And so from this green equation, we can solve for C4. And this is going to tell us actually that C4 is equal to minus 1/4 C2. And from the black equation, we could solve for C3, and this would tell us that C3 is actually equal to 2C1 if we were to solve for C3. So using all of that information, we now have our solution for for y, which is, well, I can replace C3 with 2C1, and that was the term that is in front of the e to the minus 4t. And then I know that C4 is minus 1/4 C2 e to the minus 2t. So here would be our solution, our general solution for y, and our general solution for x we started with over there. And so if you've had a lot of exposure to linear algebra and eigenvalues, let me just say that these relations between our coefficients, our arbitrary coefficients, are related to the eigenvectors for each of these two eigenvalues. So for example, the eigenvalue of minus 4, you can see in front of the e to the minus 4t term, there was a 1c1 and a 2c1 over here. So what we could observe here is that this eigenvalue lambda is equal to minus 4. It has an eigenvector which is 1, 2. And this other eigenvalue, which was minus 2, it has an eigenvector which is 1 minus 1/4. So the connection between these coefficients, if you've seen some of this in linear algebra, is related to finding the eigenvectors. Let me just say, I'm assuming that people in this course have not necessarily seen this, so that's not the approach I'm going to take. I'm going to take the approach where we find one solution, we plug it into one of the differential equations to get the other solution. The textbook goes through how you can find these by finding the eigenvectors, and you're free to use either the method that the textbook uses or the method that I'm using by substituting my templates for x and y into one of the differential equations to find the relations between the arbitrary constants. Okay, so let's move on and take a look at another example.